happy Tuesday. We looked at vectors then. We added vectors. We did scalar multiplication. We did component form, standard unit vectors. But we didn't talk about products. That is $1.09.
Sorry, your camera.
Now it's $5. We're going to look at products next, and there are two that we look at. Starting with dot product. My goal is to get through both products today. We'll see how ambitious that goal is. So let's say we have two vectors, u1, u2, u3, and v1, v2, v3. The dot product is the sum of the product of the components. So it's u1, v1 plus u2, v2 plus u3, v3. Notice what kind of quantity the dot product gives you. It's the quantity. So dot product is also called the scalar product. Nice. Properties of the dot product. Three vectors, u, v, and w, and we have a scalar c. The dot product is commutative. It distributes across vector addition. It is associated with scalar multiplication. You take any vector, dot it with itself, it's the square of the norm. So vectors will have angles between them. Right? The angle is just defined as the angle that's formed when you put initial point to initial point, so they have the same initial point. Right? So tail to tail, then the angle is just the angle that those two vectors made. Well, there's a relationship between the angle of the vectors and the dot product. U dot v is the magnitude of u times the magnitude of v times cosine of the angle between them. What does it mean for vectors to be orthogonal?
They're at in 2D, they're at 90 degrees from each other. Just 2D.
Sorry.
Just 2V.
Well, I guess they're always at 90 degrees. They're perpendicular, right?
Orthogonality, orthogonal is a fancy way of saying perpendicular for vectors. So orthogonal vectors are just two vectors that make a right angle. What's the cosine of a right angle? So vectors are orthogonal if and only if their dot product is 0. And there's a third way to say perpendicular too that we'll look at. Normal. Well, wouldn't we be interested in the angle that a vector makes with the standard vectors? These should be called your direction angles, your direction cosines. So alpha is the angle made with respect to the x-axis, I hat. Beta is with respect to the positive y-axis, the j hat. And gamma is with respect to k hat, the positive z-axis. Obviously, if you're only in 2 dimensions, then you just have alpha and beta. There are times, especially in physics, where we're only concerned with how a vector behaves in a specific direction. So what we want is its projection onto that direction. This is really true when you look at slopes and friction. Friction resists the force of gravity. Static friction resists the force of gravity in direction and slope. So you need a vector projection. Vector projection of v onto u, vector that has the same initial point as u and v, and the same direction as u. It represents the component of v that acts in the direction of u. The length of this vector is called the scalar projection of v onto u. There's the formula for finding that projection. So that's the vector projection, and this would be the scalar projection.
That's how it sounds to you. It's the magnitude.
Magnitude, yeah.
That come. What is that short for? What is that? Is that short for anything?
So that's the scalar projection.
Okay, we just call it. We just use that word to refer to it. Okay.
Now, of course, how can we use this in physics? So many ways. In Calc 2, we studied an application of integration, didn't we? Called work. On Calc 2, you made an assumption that you're moving in a single direction. You're one-dimensional. Who says it has to be phase? Well, as with single-dimensional work, you had two cases. You had a constant force being applied, right, or a variable force. Generally speaking, we have the same rules here. A constant force and a variable force. However, in general, the variable force breaks down into two broad categories. It is a force that varies only with respect to time or with respect to position. If it's with respect to position, that is typically called a force field. And we'll examine force fields this semester. For now, let's say we have a constant force being applied to an object. So the object moves in a straight line from point P to point Q. Once again, we're assuming a straight line. This does not necessarily have to be the case. And again, examine the case where it's not a straight line. The work done by the force acting at an angle theta from the line of motion is a dot product. It is F dotted with your directed line segment PQ. Of course, that angle is needed if you only know magnitudes. If you only know the magnitude of the force, not the force vector itself, you need that angle. Standard units for work is what? Joule. What's another common one used? That isn't joule.
Did they say that's right?
Hmm?
Did they say that's right?
Engineers, yeah, they use empirical units, not SIs, because they have to be
Kilogram meters.
Now, coulombs is charge. It's a unit you are very familiar with. You may not think of it as work. Calorie. Work is energy. So you may also see calories. Resolve A into parallel and perpendicular components with respect to B. The parallel component. Is simply the projection of the vector, in this case A, onto the direction B. Dot product, B dot A, over the magnitude of B squared times D. What is the dot product? B dot A. It's 15. Three times 4 plus 1 times 3. What's that magnitude? Squared. Except, so I have here, which means I'm like, oh, I'm sorry, square root of 10, yes. That makes more sense. So 15 over 10, 3 halves. That would be our parallel.
Is this the same thing we would get if we made B into a unit vector and then multiplied the magnitude of A to the, and then just like took use the angle and the
Maybe not. B is unit multiplied by the magnitude of A. That's not, that shouldn't be the same thing.
I'll mess around with it. I'll put it out of mind for now.
As a general rule of thumb, you want your answer to be in the same form. So there's the parallel component. The perpendicular component of A would be the component that is perpendicular to B. Parallel component and the perpendicular component, when added, have to give you the original vector. Four minus 9 halves, and 3 minus 3 halves. That would be it. So work done in moving an object along the vector 3i plus 4j if the force applied is 2i plus j. Oh, that was nice. Just that not product. What's that dot product? 10. 3 plus 2, or 3 times 2 plus 4 times 1. And we don't know units, so. Find the angle between these two directed line segments.
In general, we can always take O to mean the origin, right? Okay.
So how can we represent that directed line segment? The component form of OP. What about OQ? So angle between them. Well, we know that relation. So if we solve for cosine of theta, we'll wind up with that. So that's another relation. Specifically, that's the relation for the angle. What is that dot product? You don't want letter. Dot product should always give you a scalar. -7. So 2 minus 6 minus 3. What is the magnitude of OP? What about the magnitude of OQ? Cosine of theta is negative 1/2. What's theta? How'd you get it?
I didn't say that.
How'd you get it?
Well, it's negative. And
Cosine.
the only way to get the adjacent one negative 1/2 is to go 4 pi over 3 angles from 0.
They're not mathematically correct.
Am I actually incorrect? Okay.
Cosine of 4 pi over 3, I do agree, it is negative 1/2. Which is what? Two pi over 3. So why is 4 pi over 3 not a solution? Why is it outside the equation? Okay, but why does theta have to not be 1 over 3? Not negative pi to pi. That's the entire unit circle. 0 to pi.
So I skipped it. Missed it, right?
True, but who says I'm taking? Who says I have to take the first cosine? The solution to cosine of theta equals negative 1/2 is infinite. 2 pi over 3, 4 pi over 3, and all multiples of 2 pi added to it. So y is our only solution to pi over 3. That'd be the angle. What is that angle? Never get the terms. That would be pi radians, right? I asked this, I'm not sure about it, but by chance I mentioned it. Yeah, that's why I gave you degrees, okay.
Well, what I see and certainly
You wouldn't measure that, would you? You wouldn't measure it to be that. So the largest angle you can get would be 100. Look, would be pi radians, which would be, they are parallel in opposite directions. 0 would be they're the same direction, parallel in the same direction.
So So that formula, the cosine theta formula, that always gives you the acute, the smallest angle.
Not acute. 2 pi over 3 is not acute.
I'm sorry, the one that's less than pi.
Be careful.
Radians.
Yes. It'll always give you the positive angle less than pi.
Okay, so it always gives you the smaller angle.
Which means, going back to that discussion we had, the range of the inverse cosine is 0 to pi. So you can always just take the inverse cosine. of both sides. That is why you can take the inverse cosine of both sides. Which is why you're going to get 2 pi over 3 and not 4 pi over 3. So again, mathematically you were correct. But in terms of the actual application of the angle,
I skipped.
you skip the 2 pi over 3.
Right.
You gave me magnitudes. Where's your one? Sorry. You gave me the magnitudes of the 2 vectors.
Well,
How'd you get it?
the first one, both the two magnitudes on the bottom are the same, and they're both
Why are they the same?
because the formula for magnitude is square root of the sum of each component squared. Now, so that means each one comes out to square root of 14. So you have 2 square root of 14s next to each other. That those 2 square roots cancel and you get 14.
Did you get that? Alright, so just take sum of the square of the components, square root. That's your magnitude. So each magnitude is root 14. Find the angle alpha. And you can't assume it's drawn to scale. You can't just assume that's obtuse. For all you know, that could be a right angle. How are we going to tackle this? There's actually well, you can't do law of sines. You have to use law of cosine. Right, this is the side. That's law of cosines. So yes, you could do that. That is a technique. Oh, good. You get to do law of cosine and verify that you're getting the same things I'm going to get. Because you're right, I'm not using law of cosines. Oh, by the way, we can now more easily prove law of cosines using the techniques of calculus. What's the angle between 2 points? Right. First off, 2 points will not have an equal because they're just points. But you have to remember, if you shift A to the origin, you're shifting the whole triangle to the origin, which means it's still the same bloody triangle. I mean, you're not incorrect to do that. That still leaves you the problem of how you find out. Because all you did was shift the triangle. So alpha still got to be counted. That's the way you shift it.
Well, you basically do that, but by making this thing into two vectors AB and AC, and they have the same initial point, which is at A, which probably looks like if we were to draw what you were thinking of, but it would probably look like that.
First, let's find directed line segments. Let's write them as vectors. Except for you have to use log cosines. What's the directed line segment AB? Oh, does it matter if I use AB or BA? It does. I think it's the same one. It actually doesn't matter because it's still the same line. It's just the direction. So I could argue by taking absolute value, because I think I wound up taking absolute value. No, I don't. Okay. In the figure that I have, I forgot to put the arrowheads. There are supposed to be arrowheads. Yeah, they have to have the same initial point. They're going to have the same one. So yeah, if the order is going to matter. Later, it's not going to matter. So what is AB? Component form for AB. I think it's 201. Right, multiply.
You subtract the terminal point from the initial point to get for AB 1, negative 1, 0.
Yep. 1, negative 1, 0. Right, terminal coordinate minus initial coordinate. Each one. What about AC then? What's that dot product? I got negative 4. What do you get as the product of magnitudes? So what's the magnitude of AB? What's the magnitude of AC? What's their product? Yeah, you love cosine, so why would we have this discussion?
Remember,
That's
I'm looking up the formula.
wrong text. I can also consent to quiz it, it's not- That's where the second solution.
Which is one right there.
I don't care.
I'm gonna put a square.
No, it's just the magnitude times the magnitude. It squared last time, quote unquote squared, because both magnitudes were the same. That was here they're different. So what's theta? Oh, you make me sad for a cat.
Square root of 20.
Oh, you make me so sad for a cat. Since you're just happy for count two, what's my golden rule? Never approximate unless I estimate. There's your rule. Is that acute or obtuse? What is it? Cosine's negative in quadrant 2, which is larger than pi over 2. Obtuse angles are larger than pi over 2. Oh well. That's fine. Find the direction angles. So remember we have alpha, beta, gamma. Alpha is the angle that it makes with the x-axis, which is I hat. What's the magnitude of I hat? What happens if you take the dot product of A with I hat? What do you get? Just the x component, isn't it? Because I hat's 1, 0, 0. Then we have to have squared. Right. And it would actually be I squared, so that over A would be there.
Okay, I see.
What is the magnitude? Yeah, it's root 169, right? So what's alpha? Well, can I do a similar argument for beta and gamma? Be the y component divided by the magnitude. And then the z component divided by the magnitude. What is the y component? The z component? Those are your direction angles.
And this will work whichever not quadrant of the three locus. But this will work whichever octant the point is in. Okay, just like this.
Well, not point. Point doesn't make angle.
That terminal point of the vector.
The vector.
Okay.
Good? That's not what it was. So next we get to look at the cross product. Two vectors, u1, u2, u3, v1, v2, v3. The cross product, u cross v, is a vector. Its first component is u2, v3 minus u3, v2. Second component, negative the quantity u1, v3 minus u3, v1. Third component, u1, v2 minus u2, v1. Because the quantity the vector product gives you is a vector, this is also called the vector product. Could memorize that. not bad. Does anyone have linear algebra? Good. You have an advantage. You can also find cross products using determinants. You set up a 3x3 matrix. First row is your standard unit vectors, I, J, K. Second row is your first vector. Third row is your third vector. You take the determinant of that 3x3. Specifically, use a specific technique to do it. You expand along the first row. Cofactor expansion along row 1. That's how we do it in business. Ain't got time for that nonsense. Universe to solve. Technically multiverse. I'll show you that method. Properties of the cross product. U, V, and W are vectors in space. C is a scalar. Anyone familiar with properties of determinants? Please let me answer this first question. Is the cross product commutative? We have now lost commutativity. However, U cross V and V cross U are equal. They are additive inverses of each other. This is known as the anti-commutative property. So what property of determinants did I use? Say. If you flip two rows of a matrix, the determinant gets multiplied by -1. Cross product does distribute across addition. So that's nice. It does maintain the associativity property of dot products. That's the same. By the way, a very underutilized property on both dot products and cross products. Any vector crossed with the zero vector is zero. What if you take a vector cross itself? What does it mean to square a vector? How? There's two products for a vector, dot product and cross product. 0. How you set it. Okay, how you set it. It's the 0 vector.
I thought you were saying that because he sounded confused or unsure, so I was like, oh, we're talking.
This is, again, very easy to see using properties of determinants. The matrix has two identical rows. Its determinant is automatically 0. So now you can only dot vectors. You can only cross them. A scalar dotted with a vector is undefined. A scalar crossed with a vector is undefined. So we wouldn't be able to do, for instance, the dot product of two vectors and then take the cross product. That would be undefined. But you could take a cross product of two vectors and then take a dot product. That is called the scalar triple. U dot V cross W is a scalar triple product. That is the same as U cross V dotted with W. And once again, there is an easy way if you have linear algebra knowledge of finding triple scalar. It's still determinant of a 3x3 matrix, except now you don't have your first rows the standard unit vectors. Your first row would be U, second row would be V, third row would be W, find that determinant. Dot means dot product. X means, well, we don't call it X, it's called cross. Cross means cross product. We're dealing with vectors. If you're dealing with scalars, then they mean the same thing.
And under no circumstances will a dot or a cross mean anything other than multiplication. One of the things next to it is a scale. Right? Okay.
Because that would have to be a scalar product, rather scalar multiplication.
Right.
Sorry, just for clarity. That means that if we ever see like C dot U, we should assume it's multiplication, not a dot product.
That's what we mean by C.
Like the letter C, like in this situation, is a scalar.
Right, and U is a vector, right?
Yeah.
Then that would be scalar multiplication. Okay, what's called not scalar multiplication. We very rarely write it that way. We just write C.
I'm looking at the first X coordinate. I was doing 0.
cross product. So this means your cross product is in a single dimension. Specifically, it's pointing so it's pointing in the direction that's perpendicular both. So yes, it can happen. It's just your result's going to pop out in the third dimension. We had a relation between the dot product and the angle between the vectors. There's also a relation between the cross product. And you can use this to prove the law of sines. The magnitude of the cross product is the product of the magnitudes times the sine of theta. If we locate vectors u and v such that they form adjacent sides of a parallelogram, the area would be the magnitude of their cross product. Good. Definitely. Will I? Am I nice? Write a program to make a peanut butter build sandwich. Volume of a three-dimensional parallelogram. So I always forget how much it costs. With adjacent edges given by the vectors u, v, and w is the absolute value of this triple scalar product. Should be metaphorically toward. You tell me. Okay. Well, it's not actually. The order doesn't. Magnitude of the positive. They have the same magnitude, it would just be opposite directions. But we don't care about the direction of the cross product or the area. So that negative 1 doesn't stop. Torque. Again, whoever put that there needs to be target fed metaphorically. Measures a tendency of a force to produce rotation about an axis. If I want to easily close the door, where should I apply the force? Not necessarily the point, axis of rotation. The closer I get, the more force needs to be applied. There's the physics behind wrenches. The longer the wrench, the generally speaking, the easier it is. Because you're now increasing your distance from the axis of rotation. This means torque is a vector. A lot of the time when we're talking about torque, we really mean the magnitude. There is another important property of cross products, which you should be able to see in this paper. If you take a cross product of two vectors, the resulting vector is orthogonal to both. So in this case, torque is perpendicular to both your axis vector, not the axis of rotation, but the axis vector itself, and the force vector. So if you ever need a vector perpendicular to, take a cross product. Does the order you take the cross product matter if you're looking for a perpendicular vector? is the direction. Well, two vectors have just opposite direction. It's just negative. Or it doesn't matter. U cross V is negative V cross U. All that's going to do is change the direction. It doesn't change the fact that perpendicular. But if you just need a perpendicular vector, it doesn't matter how you take the cross product. The only difference is going to be which direction is the point. Area triangle that has those three vertices. That's so the area of our triangle would just be half the area of the parallelogram. So we know the points P, Q, R. We don't know what S is. What vectors do you want to use? What's QP? I see. Oh, fine. What about QR? We now need QP cross with QR. There's the first row. Second row is the first vector. Third row is the second vector. You want to write in component form. For the first component, cross out first row, first column. Determinant for the first component would be 3 times 2 minus 2 times 3. Second component is negative. Cross out the first row, now second column. Negative 1 times 2 minus 2 times negative 3. Negative 2 minus negative 6, 4. then for the final component, cross out the third column. Negative 1 times 3 minus 3 times negative 3. Negative 3 plus 9. There's your cross product. 0, negative 4 cents. It's going to be negative of whatever you calculate. So if when you do that product, you get a negative, then your J will wind up being positive. So that'll be the area. You take the magnitude of a scalar multiplication, the absolute value of the scalar times the magnitude of the vector. Scalar is 2. Absolute value of 2 is 2 times 1/2. What's that magnitude? So the area of that triangle is square root of 13 square units.
I use different vectors and got a different answer. I can come to you later.
Yeah, you should.
Yeah,
Which I would assume then that the 2 vectors you chose are not adjacent. Okay. That would be my assumption. Either that or you calculate the function. So I'll take a look. In between the I and the K, that's a J. Negative 1 times 3 minus 3 times negative 3.
Clear, like in your algebra, why J component is negative.
Yes.
Okay.
Yeah. Has to do with the minor code factor. Okay. But again, that would be so for now. I should have to say it's negative because I said it's negative.
It's fine.
And that should be actually question number 6. Why are you not? There for now. Now stay. Now squat that. Determine a unit vector perpendicular to the plane containing the vectors A and B. So let's say there's our plane. There's two vectors in the plane. So let's call that vector N. Let's say that vector is perpendicular to the plane. Then what can we say about that vector with A, for instance? How would N and A be related?
Orthogonal.
They would also be perpendicular. What about N and B? Would also be perpendicular. So if we find a vector perpendicular to both A and B, it's guaranteed to be perpendicular to the plane. Well, how can we find a perpendicular vector to two vectors? Cross product. A cross B. Or B cross A, it doesn't matter. All that would happen is the direction flips underneath. And in this case, I am not going to draw out the matrix. The -6 times -1, which is 6, minus 3 times -3. So 6 minus -9. Two times -1, -2, minus 4 times -3. So -2 plus 12, 10. Take the negative of it. 2 times 3, minus 4 times -6. 6 minus -24. There's our perpendicular vector. Oh, but wait. It asks for a unit vector. So we have to normalize that. What happens to the vector if I just give it a 5? Define what you mean by scaling. If I drop that 5, I don't change the direction, right? Get rid of 5. Because that vector is a lot easier to normalize than 15, negative 10, 30. One over the magnitude of that new vector. $49? No. 4 and 36 is 40. Square root of 49, so 1 over 7. That'll be our unit vector. That's perpendicular. You could also take the negative of that. Right? If you did, instead of A cross B, you did B cross A, all your components would just be the opposite sign is what I have up there, but it would still be perpendicular. So that would still be acceptable for the answer. Questions on dot product, cross product?
So the formula we use with cosine to get the angle between vectors, that works as it's written in any octant. Is the same true for the formula that we use with sine and cross product?
No,
Okay,
because the range of sine is minus pi or 2 pi or 2.
all right.
You want 0 pi. So you have to finagle.
Finagle it so that what you're, finagle it so that what you're using in the formula is in the first octant. Finagle it so that your theta.
If you get a negative theta, get that pi over 2.
Oh, all right.
Like this inverse sine, if you're taking the inverse sine as a negative, it's going to give you minus pi over 2, 0.
Right.
How do you get that to be between 0 and pi? You
Add pi.
right, because you want between pi over 2 and pi.
Right.
That's your corresponding.
Okay, so
That's how you do it.
if you're using that and your arc sine theta is negative, you have to add pi. Got it. Thank you.
You're going to have to so message me. I'll probably just excuse it because the discussion is not the whole point of it. Oh wait, yeah, the whole point of it was to discuss the mathematics, your experience with mathematics.
Okay.
Well, at this point, all replies are good.
Yeah, I just showed you. Sorry.
WebAssign. What browser are you using? Don't use Safari. Yeah, don't use Safari. Use either Edge or Chrome. Yeah, in fact, even WebAssign tells you don't use Safari. Yeah. Safari is not a good web browser. Safari is not a good web browser. Any Apple product does not play nice with non-Apple products. And guess what? WebAssign is not Apple. Same thing. By the way, same thing with Canvas. Do not use Canvas with Safari. Canvas specifically tell you that. Use it with Chrome or Edge. Yeah, you probably shouldn't do that either. You should just generally not use Safari for anything other than Apple stuff. As a general rule of thumb.
Okay, so what's a CAS calculation?
Computer Alpha System is what CAS stands for. So it can do some volume manipulation.
Oh wait, is that the thing you recommend? Yeah. Okay.
So 89 is also a CAS. and that's what this project requires.
Oh,
The one that I recommend is a better version.
the white one? If he does. Yeah, the one online, the one I have to work out there. The one you can fashion it.
That's the 89. That's fine.
And
I've never heard of that one.
it's the white one that, later. This one is just fashion.
That's the calculator currently requires, so that would be good enough. You don't need to go out and spend money on another calculator. That will get you through.
I know, I have like, I have this I have multiple problems.
If you prefer a different one, bring in one of the other ones you have. I can tell you if it's sufficient.
Also, one more question. The practices are magnetic, right?
Well, WebAssign will great, but I won't count it.
Okay.
It's just there as practice.
Start with a simple question. Where can I find this slide?
They will be uploaded on Canvas.
On Canvas? Okay, cool.
So the first two meetings should already be up there with the recording. Okay. This will be up there either tonight or tomorrow. Thank you.
Also, can we go over the problem? I got a different answer for it. Take a look. It's towards.
That is definitely, so they're definitely. Cross one. Your second phone should. Okay. No, positive. So it would be 1 times 0 minus negative 2 times negative 0. And then the opposite sign of that.
So, right
So that is 1 times 0, which I agree with, but then it is negative 2 times negative 2. So that would be 4. Okay. And then the negative of that would be negative 4. Not that it matters.
all right, thank you.
And I think I haven't checked your other one, but that might be, just check that calculation as well.
Yeah, I'll look back at it later.
So you got what? That was 6. So the square root of 16 and 36. Just square root of 52, right? So, which is 2 root 13. So yeah, that's correct. And then you take care of that. Yep.
All right, see you in 2 days.
Yep. Have a good day.